Hello everyone, welcome back. So now we're looking at a beam right here. You can see it. And we're doing the exact same thing we've seen last time, where we're going to integrate our equations to find out the equation of the elastic curve, as well as the deflection midway between the supports. Now this is not a simple problem, but it is definitely one that we can do. Okay, it is not a simple problem, but it is definitely one that we can do. So let's jump right into this. There's going to be a lot of integration, a lot of constants, but we'll solve for it. Let's try it out. So first off, we integrate the load distribution. Now, this is the integral. It's not a terribly difficult one, and we just keep on going up all the way. So we start with our load distribution, which is what we know. We integrate once, and then a second time, and then a third time, and then a fourth time. And each time you can see I just get that x or x squared or x cubed term. So it's not really a crazy integral. It's not very, very difficult. But how does this help us? Because we have all of these constants, so many constants. Are we going to be able to get rid of them? And the answer is actually yes. This is honestly not that difficult a problem. So we look at our boundary conditions. Like for one, we know at the free end of the beam, the moment has to be 0. So at x equals 0, the moment has to be 0. And at x equals L, at either end of the beam, the internal moment has to be 0. So from that we get, okay, well C2 is going to be equal to 0. Fantastic. We can solve for C1 using this equation. We also know that at x equals 0 and x equals L, the deflection is 0. So C4 is equal to 0. And C3 will be equal to this. We just plug everything in. And we're done. Literally, that was already it. We have finished the problem. We had 4 boundary conditions. We were already good to go. Though we don't use the moment one quite as much, but for these kinds of problems, you will have to. So, I mean, even though these problems look really hard, like you were probably freaking out, those constants are actually really easy to get. So from that, we get our elastic curve equation. It's actually really, really nice when you have a load that goes across the entire beam. It makes things really simple because you can just integrate straight from the load. Okay, so that's our deflection equation. And it asked for the deflection at the half span, so we can put in L over 2 if we want to get our deflection at the half span. And also we want to find what our support reactions are. Well, that's not all that terrible to get, because our support reactions at A and at B are going to simply be the internal shear force at points A and B. So we know that our shear force is going to be equal to the third derivative of our deflection equation times modulus elasticity times moment of inertia. So we plug 0 into our equation, and we can get the reaction force at A. We plug L into our equation, and we get the reaction force at B. And that's it. We are good to go. Glorious. So, remember, some of these problems look really hard, but like in this case, it was actually a very simple problem. So hopefully when you get to a problem, you won't be quite as intimidated. The last one, it may have looked simple, but it was actually fairly hard. This one looked really hard, but was actually fairly simple. So they can be very misleading. Thanks for listening. See you all later. Have a wonderful day. Bye-bye.